guy. This looks almost identical to the one we did yesterday, but there's a slight difference, right? The one we did yesterday, it was the same thing. It was a pasture by a river, but they gave us the amount of fencing that the farmer had. And today, that's not what they're doing. Today, they're saying, okay, the constraint is that the pasture must contain 245,000 square meters. What dimensions would require him to buy the least fencing to do that? See the difference? Yesterday, we had a fixed amount of fencing and we wanted to maximize area. Today, we're trying to minimize the fence line for a fixed area, right? Okay, and it works out. They behave a little bit differently. It's kind of nice to see both of these. Okay, so what's the primary equation here? What's the thing that we're trying to minimize or maximize? Not area. Okay, to do what though? What's the quantity we're trying to minimize or maximize? And sometimes it's helpful to just restate the question using the words minimum or maximum, or minimize or maximize. You're trying to pick dimensions to, how would you restate this right here? Say it again, sorry. Okay, yeah, good. So minimize, whatever you want to call that. Minimize, like it's kind of like a perimeter or something, right? The amount of the fence line, the amount of fencing we have to use. So what's that quantity? Let's just call it like P for perimeter. You can call it whatever you want to. So if we call it P for perimeter, what is P equal to in terms of the X and Y, the variables that they've defined for us? They already drew the picture. That was nice of them, right? And math gods gave us the variables X and Y. So what is the perimeter? Yeah, right? Okay. So X plus 2Y. Okay, what's the problem with that? Two inputs, yeah, right? So we need a secondary equation then. Well, that's got to come from the constraint, which is that, right? That's giving us an area, isn't it? 245,000 square meters. Okay, they didn't actually say the word area, but that's an area, and that's implied area. Okay, so what's the equation that gives us then, the secondary equation? Oh, there you go. Okay, good. X times Y equals the area, which is 245,000, right? Okay, so which variable would I solve for? It doesn't really matter, right? Makes no difference. They're pretty much interchangeable. I'm just going to go ahead and solve for Y. So Y equals 245,000 divided by X. I'm going to put a box around that because that's my substitution equation. Okay, now look, we notice something here. Look how Y and X are related. Inverse. It's an inverse relationship like we'd expect, but notice that we have an X on the bottom here, right? Right away, that's kind of a little bit of a red flag for us. So when we're doing the domain for this thing, can X equal 0? Can't equal 0, can it? Right? Because if X equals 0, as X gets small, Y gets big. And if X were to go to 0, that would mean Y would be going to infinity, right? Which we can't do, right? So that's just a little, when you start to see that, when you start to see an equation where a variable is on the bottom, even if it's the substitution equation, there's a little bit of a red flag saying, okay, well, that variable can't equal 0. At some point, I'm probably going to have to pay attention to that, right? So if we make our substitution, then what do we get? So P is equal to X plus 2 times Y, and there's my Y, 200 445,000 over x. So then this, look what we got. We got p as a function of x. That's good. And if I just distribute that, I get what? I get x plus 490,000 over x. There's my function p of x. Okay, let's get the domain. Minimum value for x. I mean, 0, but it can't actually be 0, right? So we'd want to do parenthesis there instead of brackets. And again, it can't be because of this, right? Or right there. Look, there's an x in the bottom right there. It can't equal 0, but it could be approaching 0. What about on the other end? Okay, so as x gets big, y gets small and vice versa. Okay? So as y approaches 0, and again, y could never actually be 0, what would x approach? As y is approach, what's the only way that we could get y to approach 0 there? If x were to do what? Get really big, right? So is there an upper limit to the value x could have? Like if I pick a trillion for x, right? That's going to give me some small number, which is going to make y very small, but y could get smaller if I made x bigger, couldn't it? So what is the upper limit of my domain? Infinity. Yeah, now it can't be infinity, right? Infinity is not a number, but this tells us that that's the domain. So x could just be any positive number. That's a little bit weird, isn't it? To think about it that way. That's not what happened yesterday. Think of it this way, though. What if I were to take something like, what if I were going to take a liter of fluid and I wanted to make a puddle out of that, a round puddle seen from above? If I squeeze that puddle down further and further and further, so it gets thinner and thinner and thinner, what's happening to the radius of the puddle? It's getting bigger and bigger and bigger, right? Is there any limit to that? If I keep squeezing, now we know that that's not the way the universe works. There are molecules and things that we just can't squeeze anymore. But assuming that this fluid were some kind of Platonic ideal fluid where you could make it as thin as possible, right? If matter worked that way, then mathematically at least, I could keep compressing that and squeezing it down and making the puddle thinner and thinner, and it would keep expanding. As the depth of the puddle approached 0, the puddle would approach being infinitely large, right? We know that there's a liter of volume there, but if I make this thing 0 thickness, then in order to maintain a liter of volume, what's the only thing I could multiply 0 by and get an answer other than 0? Infinity, right? That's indeterminate. Does that make sense? How you can kind of think about that, about that inverse relationship? Give me 1 to 5 on the domain part. Does that make sense? Okay, good, good. All right, so there's our domain. Now this ends up not being a very hard problem, right? Again, the calculus is easy. You guys have already done all the hard calculus. So if we differentiate, what's p prime of x going to be? 1. And then the derivative. Now, how do I want to do this one? Do I want to use quotient rule? I mean, I could, but that's a lot of waste of energy. How would I differentiate that term? Yeah, right. I just want to make it an x to the negative 1. I want to rewrite this term as, I want to rewrite that as 490,000 x to the negative 1. Now it's an easy derivative. By the chain rule, what's the derivative of 490,000 x to the minus 1? there you get to the minus 2, right? So negative 490,000 x to the minus 2 just puts the x squared on the bottom, right? Okay. And so p prime equals 0 at when this term equals 1, right? Okay. Or I'll say when. Well, when's that? If I cross multiply, that's just when x equals plus or minus the square root of 490,000. But I don't want the minus one, right? That's not in my domain. So I get one critical number at the square root of 490,000, whatever that is, some big number, right? So when we go up to our table, then we can start to add some stuff. We've got x is our independent variable, our input variable. And perimeters the output, right? So the domain we said went from 0 to infinity. We had a critical number at square root of 490,000. That was a 0 of the first derivative. Do I want to calculate a second derivative or use the first derivative test? Either one, it doesn't matter, right? We could do either one. Like what if we used the first derivative test? Let's just do this both ways. So if I use the first derivative test, I would want to pick a test point, like a number less than that, like 10, for example, right? If I plug 10 into my first derivative, what's the sign going to be? 1 minus a huge number divided by 10 squared gives me what? Is that fraction, if the bottom is really big and the bottom is relatively small, is that fraction going to be bigger than 1 or smaller than 1? Bigger. So 1 minus a big number is negative or positive? Negative. Okay, so we could do that. And what if I took a huge number, like, I don't know, 10 to the, we'll do a Google, 10 to the 100, okay? If I did a Google 10 to the 100, well, that's going to make the bottom enormous, so that fraction is going to be close to 0, and I'm going to get positive 1 minus nothing, which is positive, right? Okay, so by the first derivative test then, what's going on with that guy? Goes from decreasing to increasing, so it's minimum. Everybody see that? Or if I'd wanted to, I could have just as easily gone over here and differentiated this again. That's probably what I would have done. Second derivative, that goes to 0. So the derivative of 490,000 x to the minus 2 is going to be positive 2 times that. So 980,000 divided by x cubed. But the point is, for positive values of x, it's always positive, right? So we could have just as easily done that. Take your pick. And that would have just given us a plus there. Either way, we're getting a minimum, okay? So if there's only one extremum in our whole domain for a function that is continuous, where's our function? Right, oh, right here. That's continuous on our domain, that's got to be the absolute minimum, doesn't it? Right? There's no other way we could get a smaller number. So we found it. The square root of 490,000 is the value of x. To find the value of y, I just go right back up to here, right, and plug it in. And what's that give us? If we plug those numbers in, let's just use decimals. We'll just round this thing. This farmer's not going to be that precise about this. What's that? Oh, it is. Okay, so 7. Oh, that, I guess that makes sense. Huh? So the square the square root of 490,000 is 700. So then 245,000 divided by 700 is 350. Yeah. So we end up with our dimensions being 700, and then this would just give us y equals 350. So did the shape change from yesterday? Wasn't yesterday, didn't we get a rectangle that was twice as wide as it was, right? Where the x was twice as big as the y? So the aspect ratio, right, stayed the same. The relative sizes of the two fence lines, the parallel and perpendicular, but we had different conditions, and so the quantities changed. Doesn't that kind of make sense, though? Think about this just conceptually for a second. If we have a fixed amount of fencing and we want to maximize the area, aren't I looking for the most efficient way of containing area with these parameters? Another way of saying that would say, okay, well, if I have a fixed area and I want to minimize the fence line, I'm also looking for the most efficient way of containing the area, right? So it's not surprising that the shapes are the same. Okay? Give me 1 to 5 on that. Is that making sense? I mean, it just takes a little practice, and you guys are about to start practicing on this. I just wanted to get through a few baseline examples, and then now you'll be able to get going on this. One more for today, and this is a pretty cool one. I like this one. There's an interesting, you can always extend this thinking on these things a little bit, and I think it's always kind of interesting to do that. There's some implications that are somewhat profound here. 4 feet of wire is to be used to form a square and a circle, right? So we're going to cut the wire and we're going to bend it into the shape of a square and the shape of a circle, okay? How much of the wire should be used for the square and how much should be used for the circle to enclose the maximum total area? Okay, this is kind of interesting. How are we going to set this up? Depending where you cut it, if I cut it like, I guess I have the option of not cutting it at all too. Okay. Let's see what the math gods tell us here. So if we know that the wire is 4 feet long, this represents our wire. How about? From there to there is 4. What's our variable going to be? And when you think about the variable, the word vary is important here. What's the thing that we can vary or control? The only thing that we can control in this whole problem. It's the only thing we can control. So it's saying we've got 4 feet of wire and we want to build these two shapes. We want to build a square outline and a circular outline. Yeah, I'm going to cut this into 2 pieces, right, and just bend one of those into a square and one of those into a circle. You mean area, you mean? Well, maybe. We can speculate, but I guess we'll see what happens. That's what you can vary, isn't it? Right? How much wire you're using for each shape, but you only have 4 feet total, right? So let's call it X. That's a convenient variable. Let's just say that this distance right here then, if we cut, we're going to call that X. That's the amount we're cutting for one of the 2 shapes, okay? Which one would be easier? I don't think it matters. I don't think it really matters. So we've got X. How much does that leave over here then? What's this amount? 4 minus X, if the whole thing is 4, right? Okay. Let's just say that we're going to take the X and we're going to bend that into a square arbitrarily. right? So this part is going to give us a square. And what's going to be the side length of that square? What is it? X over 4. Yeah, right? That's going to be the side length of our square. And then over here, we've got our circle, right? And what's the perimeter of our circle there? 4 minus x. Okay. So the perimeter is 4 minus x, or the circumference, I should say, right? The circumference of our circle is 4 minus x. So what's the radius then? What's circumference equal to? There's an easy way to remember circumference because it's a unit circle thing, right? Unit circle means radius of 1. And remember, on the unit circle, radians measure how far you've moved actually along the unit circle. They're not actually a measure of angle per se. They're a measure of subtended arc length. So if we go all the way around the unit circle, and that takes 2 pi radians, and the radius was 1, what's the circumference is just 2 pi then, right? Does that make sense? Okay, so it must be 2 pi r, right? Because we multiplied by 1, which was the radius. Does that make sense? Right? Circumference is equal to 2 pi r, but for the unit circle, unit means 1, the radius is 1. That's how we get 2 pi. Okay? Okay, or you can just remember that formula. Either way, 2 pi r circumference. So if we want to solve for radius, then I'm just going to divide each side through by 2 pi. And so the radius of this thing is just, is 4 minus x over 2 pi, right? Well, those are the pieces I need to add up the individual areas. And the total area is just the sum of the two areas of those shapes we're creating, right? So our total area, our area function, is going to equal, what's the area of that square? How do you calculate the area of a square? Okay, yeah, side length squared. So x over 4 quantity squared. So that's just going to be x squared over 16 plus the area of the circle is just pi r squared, right? Okay, so that's going to give us pi r, which is this thing, squared. So pi times, we'll square the top, 4 minus x, quantity squared, and we'll square the bottom. 2 pi squared gives us 4 times pi squared, right? And then we could cancel a pi and just get that, okay? Well, look, we've got area as a function of only one variable, which is x. Okay, that makes sense? Let me pause there. That's a lot of stuff. Let me pause there. Everybody get that? So again, just to summarize, right? Because we're trying to maximize the enclosed area, right? So we start with 4-foot wire. So we're going to cut off a length that's x long for the square, which leaves us a piece that's 4 minus x for the circle, right? So x is our perimeter of the square, and 4 minus x is our circumference of the circle. But to calculate areas, we need the side length of the square and the radius of the circle. So we can calculate that, right? The side length would be 1/4 of x. Each side is going to be 1/4 of x, adds up to x. And over here, if the circumference is 4 minus x, well, that equals 2 pi r. So we just solve for r to get r. And then we use our area formula, pi r squared, to get the area of the circle. right? Okay, so now, what's the domain of this thing? X is our variable. What's the smallest that X could be? And again, think what X is. X is just how far we're going from the left edge of our wire to snip the wire into two pieces. What's the smallest value we could pick? 0. We could pick 0 too, couldn't we, right? There are no X's on the bottom anywhere in here. So 0 is fair game, right? We're not dividing by 0. So our lower limit is 0. What's our upper limit? What's the furthest to the right we could go to make our snip? 4, right? I could go clear to the end and I could make it 4. Or I could snip somewhere in the middle. So that's our function. Look at that. That's not horrible, right? We've got a function there that's just got x's in it. We could simplify that function a little bit. How about if we expand this out, a of x is going to be x squared over 16 plus 4 minus x quantity squared. Isn't that just x squared minus 8x plus 16 all over 4 pi? Right? Everybody buy that? And then I could split this into separate terms if I want to. How about I could even, if I want to, I could even get a common denominator here. That'd be fine. I could multiply this one by, I could multiply that fraction by 4 over 4 to get 16 pi on the bottom. And I could multiply this one by pi over pi to get 16 pi on the bottom if I want to, right? It's another way to look at this. And then I end up with pi x squared, if I distribute the 4, plus 4x squared minus 32x plus 64 all over my common denominator of 16 pi. I just pull that common denominator out front and think of that as a constant then, right? And just differentiating this then is pretty easy. Let's pull the constant out. And I could combine those into one term if I want to also. Those are like terms. But let's not. So there's our function, and we have our domain. So let's differentiate. So what's A prime? Okay, we leave the constant out front. Good. Derivative of that term? Okay, 2 pi x. That term? 8x. Okay, minus 32. And then that one's 0, right? Good. Okay. So let's go ahead and take a second derivative because we can already see what's going to happen here, can't we? If I take a second derivative, I leave my constant out front, and I'm just going to get 2 pi plus 8, right? So for any value of x in our domain, in fact, any value of x anywhere, what's the sign of that? There isn't even an x in our second derivative. Is it positive or negative? It's positive. Okay, so we could find a critical number here. When we're done with this problem, let's go back and we'll go back and ask ourselves, did we even need to bother with that? Can we see a reason why we don't need to? What are we trying to find here? We're trying to maximize the area Ah, yeah, the concavity is always positive. So any interior critical number is going to be what? Minimum or maximum? By the second derivative test. It's going to be a minimum, isn't it? So do we care? I mean, any critical number that we get is not going to be valuable to us because we're not looking for a minimum area. We're looking for maximum area, right? I mean, we could find it. Like if we just go up here, like if we were to go through right here, if we were to solve this thing, a prime is 0 when this factor is 0, right? So when that factor is 0, when 2 pi x plus 8x minus 32 equals 0, right? That's when the a prime is going to equal 0. Okay, everybody good with that? So I could add the 32 to this side. Let's factor out an x. And I'm going to get some weird number. If I divide both sides by that number, my critical number is that x equals 32 divided by 2 pi plus 8. So what is that? 32 divided by about 14 point something. I'm going to get some number that's like 2 point something as my critical number, right? What is that? Somebody real quick, just what is that as a decimal? So I don't have to write that whole number down. So x is approximately equal to what? So 14.28 divided by 32. I'm just going to put, no, it's like 2 point something, right? 30, just do 32 divided by 14.28. 2.24, okay. So roughly equal to 2.24. So on our table, oh, we never made a table. Got to make a table. Here's our table. So x, area prime, double prime. Our domain is 0 to 4. We had an interior critical number of about 2.24, where the first derivative was 0, second derivative was positive. So that's telling us minimum. So we're trying to find, when we're doing an optimization problem, we're finding an absolute extremum, aren't we? Always. We just want to know what is the maximum or minimum value on our domain. That translates to an absolute extremum. So where would we look for the maxima then? Where's the maximum going to be? If the only interior critical number is a minimum, where's the absolute max have to occur? Well, at an endpoint, right? So we could check the values of the function at 0 and at 4. Okay, if I evaluate my original function at 0, where do I have a convenient? Well, I guess there's a good place to look at it right there. Okay. That's a pretty good place to look at it right there. If I let x equals 0, this is kind of interesting too. If I let x equals 0, the white term goes to 0. The yellow term is going to become 4 minus 0, which is 4 squared is 16 over 4 is 4. So I get 4 over pi, right? 0 plus 4 over pi is 4 over pi. Okay, if I use the other endpoint where x is 4, what's going to happen then? Well, then the yellow term goes away, right? Because I get 4 minus 4 is 0, and I just get 1. I get 4 squared over 16, which is 1. Okay, which is bigger, 4 over pi or 1? 4 over pi, right? Because 4 is bigger than pi. But isn't that interesting? If I let x equals 0, the white area, well, what's the white area? That's the square, right? That's the piece we use for the square, goes to 0, and it's all circle, right? If I let x equal 4, clear down here, then the yellow part goes away, and it's all white area, right? Which means it's all square. So when it's all square, when x is 4, the area is 1. When it's all circle, the area is 4 over pi. So and your intuition probably told you this from the start. What's the most efficient way to enclose the most area there? Bend it into one big circle, because circles are more efficient than squares at enclosing area, right? Isn't that interesting? And so if you were to do, like, you could extrapolate this thinking, and what if you thought about, like, okay, so if we were going to compare, what if I were going to do like a square and a triangle? What do you think would happen then? Square would be better. What if I did a square and a pentagon? Pentagon. You could even identify, if you wanted to do something pretty theoretical here, you could even do something like define, like a pointiness index. Like, how pointy, if I make a regular polygon, how pointy is each vertex? And the less pointy it is, the more circular it gets, the more area that it's going to contain, right? So this is the two-dimensional version of this problem, where we're talking about enclosed area. What if I expanded this to 3 dimensions? What would I be talking about then? Instead of enclosed area, enclosed volume. We could have done this same problem with let's say we've got this membrane that we can reconfigure to make a skin or a surface, and I'm going to spend this fixed amount of area. I'm either going to use that to construct a sphere or a cube. Well, who would have won? Which one would have enclosed the volume more efficiently? The sphere would have, right? We could have done, it would have been a harder problem, but we would have had the same result. Okay, that tells you something kind of interesting. Think about the shapes of animals, of mammals that are warm-blooded, that have to maintain a body temperature. Okay, what would you expect if you've got mammals living in really, really cold environments, like in super cold waters? How are they going to survive? They've got to maintain a body temperature. Well, where do they lose their heat? Through their surface, right? That's where they're in contact with the cold water. So what would you expect then? What shape would you expect those kinds of animals to have if they want to have minimal surface area for maximal volume? They're going to be kind of spherical, aren't they? Well, whales, walruses, I mean, right? Those are kind of, see what I'm saying? What if you were the opposite? What if you were a mammal living in an extremely hot environment where you wanted to have maximum surface area for minimum volume because you want to be able to cool yourself, right? Well, it's why, like, if you were to look at animals that live in desert environments, they're going to tend to be long and lanky. Elephants cheat because their ears are radiators, so they're kind of cheating. And hippos stay in the water, so they're cheating too. But you look at, like, little mammals, they're always kind of pointy. Yeah, well, they're cold-blooded.